electrostatics. So once all of you just listen the problem. A positively charged small disk is released on the top of fixed hemisphere and it is frictionless in the presence of a uniform horizontal electric field. If the disk leaves the dome after an angular displacement theta is equal to sine inverse 3 by 5. Find the ratio of gravitational and electrostatic forces on the disk. Assume that the dome not exhibit any electrical properties. So this is the electrical dome here. So this is the dome and this dome is not having any electrical properties, and you can clearly see there is a positively charged disk placed on the top of the dome and the electric field is applied in positive x direction as shown in the figure. And at the angle theta is equal to sine inverse 3 by 5, this small disk may lose contact with the dome. So here we are required to find out the ratio of gravitational and electrostatic forces on the disk. So now let us proceed to the solution. So I will show you the schema drawing diagram for the problem. So this is the diagram for the problem. You can clearly see here the electric field is acting in positive x direction. So this is the positive x direction and this is the negative x direction. Electric field is acting in positive x direction and it will definitely exert some force on a positively charged disk because this disk is positively charged. So due to that reason the disk will gradually slide on the dome, and whenever it reaches to the point B, so at the point B it is going to leave the dome. That means in the direction of velocity it will going to leave the dome. It will travel like this. So like this it will travel and it will may fall like this, and it will leave contact with the dome at the point B. So this is the situation. Okay, now let us see how to solve this problem. So first of all we have to observe the forces acting on the disk at the point B. So I am going to take the normal force and it is acting perpendicular to the direction of velocity at the point B, and F is equal to EQ is the electrostatic force which is acting in positive x direction, and mg is the weight of the disk which is acting in downward direction. So I am going to apply Newton's second law at the point B. Let us see how I am writing that equation. Now I am going to take the component of weight which is in the radial direction, so that is mg cos theta. So here this force component is mg cos theta. Okay, this is the force, and normal reaction is acting perpendicular to the direction of velocity at the point B and it is upward direction. And you can also take the component of the electrostatic force in normal direction, that is F cos 90 minus theta. So now net force at the point B must be equal to mv square by r. So now I am writing that. So just see the mg cos theta minus n minus f sin theta is equal to mv square by r. This is the equation that I can write at the point B. But in the problem it is clearly mentioned that it is going to lose contact with the dome at an angle theta. So at this particular angle theta, so theta also clearly mentioned, theta is sine inverse 3 by 5. So at this particular angle it's going to lose contact with the dome. So that point is very important. And here if the disk lose contact with the dome, if disk lose contact with dome, then normal reaction must be 0. Normal reaction must be 0. Okay, so that is very important. The normal reaction must be 0. Okay, so now I'm going to write that point here. So whenever it going to lose the contact with the dome, the normal reaction at this point B is 0. So I'm going to substitute there, and here the theta value is given as 3 by 5. So what is the value of cos theta? So cos theta value will be 4 by 5. So I'm going to write that one also here. So mg into 4 by 5 minus normal reaction is 0 and f is equal to eq, and sin theta value is 3 by 5 is equal to mv square by r. So this is equation number 1. Next, so we have to consider another important equation here, that is the work energy theorem. You can apply work energy theorem from A to B. So what is that? Work done by all forces is equal to change in kinetic energy. So you can apply this work energy theorem. Work done by all forces means work done by normal force plus work done by gravitational force and work done by electrostatic force. That all work done must be is equal to change in kinetic energy. So this is work energy theorem. So we are going to apply this work energy theorem. So now see what we will get. So here work done by normal force is always 0 because normal force is perpendicular to the direction of velocity. So it is 0. So work done by weight mg, work done by weight mg can be calculated as force into displacement in the direction of force. So displacement in the direction of force is AC. AC is the displacement in the direction of force. How to calculate this AC? AC can be easily calculated. AC can be written as AO minus OC. AO minus OC. AO is R, OC is, what is the value of OC? OC is R cos theta. OC is R cos theta. You can directly write that here. And the AC value we are getting as R into 1 minus cos theta. So this is the value of AC. We can plug it here. So now the work done by gravitational force is mgr into 1 minus cos theta. That is the thing that we are getting. And work done by electrostatic force can also be calculated. Work done by electrostatic force is equal to F into the electrostatic force into the displacement in the direction of electrostatic force, that is BC. So BC is the displacement. But what is the value of BC? BC value is R sin theta. Just by observing the triangle we can say the BC value is R sin theta. This BC is R sin theta. Okay, so now we can plug it here, and F is equals to EQ, BC is equal to R sin theta. So this is the work done by electrostatic force. So we have all the work done, so we can equate to change in kinetic energy. So what we can write? So mgr into 1 minus cos theta. So this is the work done by gravitational force plus work done by electrostatic force is EQR into sin theta. So these are the total work done. Now that must be equal to change in kinetic energy. Change in kinetic energy is nothing but final kinetic energy minus initial kinetic energy. But final kinetic energy is half mv square, initial kinetic energy is 0. So here we can write the same mgr into 1 minus cos theta plus EQR into sin theta. But the thing is here, what is this cos theta? You already know the value of cos theta here. Cos theta is 4 by 5, sin theta is 3 by 5. So I'm going to put the values here. So mgr into 1 minus 4 by 5 plus EQR into 3 by 5 is equal to half mv square. So here we can see this mv square. From this we can clearly write that mv square. So this multiplied by r. So that is mv square. So just I'm writing that. So I'm just taking that equation and pasting it here, and if I multiply this with r, I will get the mv square value. So just I'm writing there, and I can find out now the value. This is 5 by, so 1 by 5 into mgr plus this is 3 by 5 into EQR is equal. So this is so yeah, 2 by 5 mgr minus, and this is 3 EQR divided by 2 into 5. So now you are going to take the EQR terms one side and mgr terms other side, and let us see what we are getting. If you take this term this side, so this is 3 by 5 EQR plus 3 EQR 2 into 5 is equal to 2 by 5 mgr minus 1 by 5 mgr. So this thing what we are getting is 1 by 5 mgr, and this what we are getting is 3 by 5 EQR is taken common, and this will becomes 3 by 2, And finally this are going to get cancelled out, and 5 going to get cancelled out. So 9 by 2 is equal to mg divided by eq. So this is the thing finally we are getting. So the ratio of gravitational force to the electric force is 9 by 2. The ratio of gravitational force and electric force acting on the dome will be 9 by 2. So this is the answer for the problem. I hope this lecture is very clear to you. So thank you for watching.